Quick introduction. Thank you for attending this talk and having me here. Quick introduction about myself. My name is Badri Rajasekar. I work for a company called TalkBox, and for those of you guys who don't know, TalkBox provides an API platform which enables application developers to sort of integrate face-to-face video in their HTML5 applications or native applications. And we are built on WebRTC, and so hence the title of my talk, and that's why I'm here, is to basically talk about face-to-face video and how to solve these real-world use cases using WebRTC. Quick show of hands before I start. How many of you guys are either building WebRTC applications or know what WebRTC is? Quick show. Okay, so we've got a good audience of people. Firstly, if you're wondering what the title of my talk didn't make a whole lot of sense, it's actually a riff off of this old security hacking journal. And there was an article called Smashing the Stack for Fun and Profit, which spoke about like stack overflows, and I basically riffed off of that for my title, but it's got nothing to do with security. I'm going to be talking about WebRTC and what it takes to make WebRTC happen. At a very high level, what I'd like to do is to provide a flavor for what WebRTC provides out of the box, and what the APIs look like, and walk you all through certain common use cases that it enables, and also potentially look at some higher level or more complex use cases, and provide a flavor of all the considerations which it might be worthwhile as developers to look at in the context of enabling these much more complex, rich WebRTC applications. So at a high level, WebRTC is essentially real-time communication APIs for HTML5. It's a whole series of APIs which were designed to enable real-time communication in HTML5, and at the highest level, it's a series of APIs which enable browser-to-browser real-time communication. And I think and this is sort of important because in the past, the only way you'd sort of implement browser-based real-time communication apps would be one of two options. You'd either build a plugin, you'd build your own plugin which is installed in the browser, and you do real-time communication with it, or you would use Adobe's Flash. So you would use something like RTMP or RTMFP for live streaming, and you would basically build it on the Flash player. Now, there are a lot of Adobe people in this conference, so I'm not going to talk about Flash or RTMP or what the problems are there with RTMP, but it's sort of useful to note that WebRTC is designed from the ground up, taking into consideration a whole host of problems which need to be solved in the context of real-time communication. And it's got a whole host of backers: Mozilla, Cisco, Google, Ericsson, what have you. And so a lot of industry momentum behind WebRTC. Slightly lower, not only is it sort of the standard for browser vendors to enable WebRTC, it's also packaged on a whole slew of existing standards for real-time communication. So if you look at a peer-to-peer protocol, that's basically three fundamental phases. There is the session negotiation phase, where you need to be able to communicate across the peers to say how exactly you connect to a session. There is a media phase, where you need to start encoding the media, decoding it, figuring out all the parameters associated with media. And there's a connectivity phase. As soon as you negotiate a session, you also need to be able to provide and do connectivity checks. Can those endpoints indeed be connected? And if so, how should they be connected? And as you can see here, there's a whole host of very well understood standards which underlie a lot of what WebRTC is designed to do. For session negotiation, we follow SDP and the offer answer model. There's some contentious debate about if this is the right model. If you guys are from the SIP voice over IP space, you'd sort of be familiar with all of these technologies. For media transport, we essentially use secure RTP, so it's fully encrypted audio and video. And for connectivity, we basically use ICE. So ICE is a framework for NAT traversal, which enables people to cross firewalls. Now, this is obviously a very important consideration when you're building any sort of real-time communication app, especially with WebRTC. And we'll sort of delve into a lot of those a little bit into the talk. So like I said, WebRTC is quite prevalent. There's a whole bunch of browser vendors who have sort of committed to taking it forward. If you look at the state of union of where WebRTC is at, Google and Mozilla are very heavily backing WebRTC. So the current versions of Google, current versions of Firefox support WebRTC. And on mobile fronts, it's a little bit fragmented, right? Chrome on Android and Firefox on Android support WebRTC, but there's not a clear solution or path for what to do about native applications in mobile browsers. What is also conspicuous by its absence here is basically Safari. So Apple, as far as at least I know, has no public stance on WebRTC. So we don't know what their stance is, what kind of codecs they want to support, when they're going to implement it in Safari or iOS. We have no idea. The other actor in this, who's also a little bit conspicuous by lack of support, is Microsoft. So Microsoft, if you look at IE, does not support WebRTC, although they say that they are behind the standard. They do have an alternate proposal to the standard called CU-RTC Web. And I'll talk a little bit more about how that fragmentation is actually causing problems in the ecosystem. But the key takeaway from this is there's a lot of heavy-duty industry backing to WebRTC, and it's definitely going to become very prevalent soon. So what I'd like to do is sort of delve into a very simple example of what it takes to set or use WebRTC out of the box in a peer-to-peer context and go through the call flows, and also talk to you all about, given the functionality of WebRTC out of the box, what are these sorts of sample applications you can build off of it. So let's go through a very simple example. It's the standard example. Alice and Bob want to talk to each other, but they're modern day Alice's and Bob's, so they have modern browsers, and they want to be able to use the browser to sort of communicate across each other. So that's the high-level use case it's designed to solve. And WebRTC, like I said, is inherently a peer-to-peer protocol. So it's one-to-one is what it's designed to solve at this point. And like I said, if you look at the high-level phases, you can sort of split it down into certain fundamental steps. You first need to be able to gain access to the camera and the microphone or any appropriate input device. You need to be able to negotiate between endpoints and say how exactly you're going to establish that connection or what the initialization parameters are. You need to actually check that connectivity and ensure that those endpoints indeed can be connected, and if so, how they can be connected. And once the connection is established and both sides have finished their handshake, you can actually start sending media. So to quickly delve into some code examples as we walk through these use cases is, let's say Alice and Bob want to connect. The first step is obviously to create a peer connection object. And a peer connection represents as the name implies, a sort of peer-to-peer connection across two clients. Once you create a peer connection, you see some configuration information there where it says stun and stun.example.org. Let's just ignore that for now. I'll talk about that in the connectivity section. But for now, just assume that you're basically creating a peer connection object. And all of these are native WebRTC APIs, which browser vendors support. Once Alice creates a peer connection object, you obviously have to go to the first step and say, okay, can I grab access to the device or camera or the media? And what you basically use is the get user media API. And what get user media does is grabs access to the device and initializes a stream. So in this case, you see audio and video are true, which means in this example, I'd like to create an audio and video stream together. And the stream has been initialized by creating an object URL from it. And once the stream is available, it can be rendered in the local view without publishing it to the external world. I can just look at the input feed from the camera and the microphone. And in this case, I've basically added it to the peer connection object, which means my intention is to sort of establish it to the associated peer. Once I do that, here's where the SDP part comes into account. You need to be able to negotiate a handshake with the other end to say, I initialize my media parameters with all of these variables. This is a sort of audio codec, this is a sort of video codec, this is what I need to do. And for doing that, you create what is called an offer. So again, people from the VoIP world, you'll be familiar with the offer answer. In this case, we create an offer which Alice can then send Bob. So we've created an offer at this point. Once you create an offer, you also set what is called a local description, which basically says, I'm going to inform my browser that this is what I have agreed upon, and I'm going to communicate to Alice. So you create a local description, and you have to send the offer somehow, in this case, magic pixie dust. I'll talk to you guys about why that's the case, but just assume for the sake of argument that I have a mechanism to somehow send the offer from Alice all the way up to Bob. Bob receives the offer from Alice. Again, we have magic pixie dust. He's very excited to get an offer from Alice. And what he does in response is he creates a peer connection too, and then sets the remote description. Basically what it is he has got an offer from Alice, and Bob now says this is what Alice said in her end in terms of initialization parameters. Once he has initialized his local description, what he does is he then creates an answer. Obviously, Bob has to respond to Alice if he wants to talk to Alice, so he creates an answer in response to the offer. Once you create an answer, you've got to be able to send it back to Alice. And that's what Bob does. Bob sends it via, again, magic pixie dust here. And if you see in the bottom right of the slide, there's a whole series of things this triggers off. This triggers what are called ICE connectivity checks. It triggers the DTLS handshake to negotiate, the keys for how the media is going to be encrypted. But for the most part, you can assume that, Alice is now got an answer from Bob, and she's willing to sort of proceed further. At this point, Alice has got an answer. What she does is she then basically sets the description, and then you have an on-add stream event in the bottom. This basically says, okay, the negotiation has been complete, a stream is available, and now you can start streaming. Now this is essentially the offer answer handshake, which needs to happen between two browser endpoints in order to negotiate a peer-to-peer WebRTC session out of the box. As you can see, it's not simple, but it's not complex either, outside of the fact that there was some magic element there in terms of how do I get the offer from one endpoint to another, or how do I get the answer from one endpoint to another. It's fairly straightforward. This can actually enable a whole bunch of very, very interesting use cases and interesting applications. Just to give you guys a sort of flavor of what this might entail. So I work for a company called TalkBox, and we have teams in Barcelona, we have teams in Sydney, we have teams in New York, we have teams in San Francisco. So just like most typical companies, we have multiple distributed teams, and we have this daily scrum and the usual meetings. And what we decided to do as a proof of concept, because we are a WebRTC platform, is to build a video conferencing tool which we use internally for dogfooding. This is not publicly available, it's just an internal tool to conference across all of our participants. As you can see, it's quite powerful, it's a well-polished app. All of the conference rooms are basically named after cities. So for instance, I can tell Betsy, let's meet in Paris and talk about the design of some component. There's actually a spinning globe where we can both click on Paris and enter that room. So that's how this works. As you can see, you can, with just native WebRTC, build some pretty powerful applications. The astute observer here would ask, I did mention earlier on that WebRTC is inherently peer-to-peer. How come there are 4 people showing up on stream? How did that happen? And hold your thoughts, and I'll talk about that a little bit later on in my slide. An interesting thing about WebRTC is that it's not just about voice and video. It's truly been built from the ground up with certain very interesting APIs and primitives for solving real-time communication apps. One specific thing I'd like to point out is the data channels API. Just like in my example between Alice and Bob, I showed you a peer connection between Alice and Bob, which was established, which routed audio and video streams. There's an equivalent concept called a data channel, which is a peer-to-peer, it's exactly what it is. It's a channel between 2 peers through which I can send data. So there is no intermediary involved in this process. It's sort of a very interesting concept. There are 2 modes, basically, reliable mode and unreliable message delivery. Reliable is obviously built on top of TCP, and unreliable is built on UDP. And the APIs are quite simple, actually. You basically create a data channel on the peer connection, and you can send, and you have an on message received event. It's quite interesting, quite fast because it's UDP. And I was in a panel recently in API World where the moderator asked me, what are the most interesting applications you have seen in WebRTC? There's a whole host of very interesting applications built on WebRTC, even based on pure data. Here's a simple example. Mozilla basically releases demo app, which is a first-person multiplayer. It's a first-person shooter online multiplayer game, which is basically taking a game engine written in C++, compiling it to JavaScript such that it can run on JavaScript and WebGL, and essentially uses the data channel API in WebRTC on Firefox to basically communicate game state across players. You guys can actually try it out if you had Chrome or Firefox. The latest version is called Banana Bread, and it just goes to show the power of very interesting apps and use cases which can be built with WebRTC, even outside of audio and video. Another example which I thought was quite interesting was a peer-to-peer CDN. So this company called Peer CDN is basically the ability to serve off static assets across peers. So if I visited their website, then I become the CDN for the next person who's visiting their website, and this is completely based on data channels. I thought it was a fascinating concept to build a peer-to-peer CDN using data channels. Again, very interesting use case, quite unintuitive according to me at least, but was built on data channels. The third example is sort of secure peer-to-peer file sharing, again implemented on data channels. So you can share a file peer-to-peer using the data channel, and data channel has support for binary data as well. That's in the standard, and so you can actually stream files from one endpoint to another, which I thought was sort of a very interesting use case for data channels. As you can see, all of these, even though the primitive was simple, it's just a peer-to-peer connection, all of that, it really opens up a whole host of very interesting applications in the WebRTC space. And it's quite exciting. And we, being a platform, we're able to see all these developers build stuff on top of us and have a first-hand view of what people are building with WebRTC. It's really powerful, but there are a whole bunch of real-world use cases which require us to think beyond what comes out of the box with WebRTC. So the first half of my talk, I wanted to show you guys sort of what comes out of the box, and also walk through some interesting use cases and sort of what considerations you need to think about as you're building much more complex, immersive, multi-party experiences. Which brings us conveniently to the first topic. The magic pixie dust I spoke to you guys about, where offers and answers are being traded back and forth between browsers, is an explicit, should I say, consideration of the standard. The standard did not specify how offers and answers, and you can just think of offers and answers and SDPs as blobs of data which just need to be communicated across endpoints. Did not specify how these blobs of data are transported, and so there is no signaling specification. I think it's a fascinating move by the standards committee. It's actually quite it shows quite a bit of foresight. Although if you go to the mailing list, there's very heated discussion about what it should be, why should it be. It's quite entertaining actually. So it doesn't speak about what the options are. So there's a whole host of options which you guys as developers can sort of leverage on. You can use XMPP messages and send the blobs and the payload across different endpoints. You could use SIP. You could use SIP or WebSockets. We are a HTML5 conference, so you could use SIP or WebSockets and actually send SDPs across different endpoints. You could write your own custom protocol to be able to do it. But the bottom line is you need a third-party service, or you have to build something yourself. So there is some development work which needs to be sort of well thought out to handle signaling. Again, you could use third-party services like Firebase. I was out there in the booth and I saw the PubNub guys. That's another service which can be used for real-time messaging. You can use our service, which is called OpenTalk. You could use the Channel API in App Engine. There's a whole host of options. And the thing I would like to point out, and sort of I think an interesting consideration to think about, is it's not just offer and answer. It's not just passing these blobs about. As you're building these complex real-time applications, you might want to think about designing sort of a signaling mechanism which also takes into account the application level messaging. Let's say I was doing a multiplayer game. You would need very low latency, high sort of high frequency signaling. Let's say I was doing text chat, that would be completely different. Let's say I was using signaling for other things in my application. There are all these workload considerations which need to be taken into account as you're thinking about signaling in real world applications. Just in our own experience, because we are a platform, we had no way to figure out what the signaling workload would be. We only could model it, but we couldn't really predict it. And so we built out our own custom high-performance signaling mesh for WebRTC. That's one route you can take as you're going through signaling. So I think signaling is sort of very important to take into account as you're building this application, and not just for this, but also interoperability. Let's say your application actually wanted to interoperate with a PSTN device. Let's say I was able to call with my PSTN endpoint into a WebRTC session. You need to figure out a mechanism or a signaling protocol which is easy to interoperate with legacy systems. Maybe you will use SIP then instead of XMPP or something else. It's sort of an important consideration to sort of keep in mind. The other thing which is I think often overlooked by WebRTC developers as they're building complex applications is connectivity. Depending upon what your use case is or what your applications is, you might be behind, your customers or the people who use your app might be behind an enterprise. They might be behind very restrictive firewalls or NATs. You need to be able to do some sort of NAT traversal to be able to establish connectivity. And so WebRTC again uses two standard mechanisms. It uses stun and it uses turn. So what stun does is merely you can think of it almost as an echo server where your browser is able to ping that server and ask what its external IP is. So you'll be able to sort of ping a stun server and then use the external IP port which the stun server returns back to you to negotiate media. There are multiple types of NATs, as you guys know. Stun works in a lot of cases, but there could be situations where you're behind a symmetric NAT where even stun will not work. In that case, what you want to think about is turn. Turn is, in the simplest sense, a media relay. What it does is each end basically negotiates to relay through the turn server, and because the turn server is publicly accessible to both of the endpoints, it can use it as a relay. Let's say you're building even a peer-to-peer WebRTC application, and some of your users may be behind a corporate environment or an enterprise environment. You need to sort of think about upfront about what your NAT traversal strategy is. Let's say you're deploying turn servers. It's a non-trivial amount of effort to actually set up your own turn servers. You have to do capacity planning in terms of how many concurrent streams you're willing to support, and actually scale all of that out. And so connectivity doesn't come for free. And interoperability is also a very important consideration to think about as you all are building sophisticated WebRTC applications. And I have a pretty cool photograph here. Does anybody know what this photograph is? Have you guys seen it? Yeah? Sorry? Yeah, that's right. It's in the Vatican. This is the funeral of Pope John Paul II in 2005. This is the inauguration of the new Pope in 2013. And that was 2005. That was 2013. So we are in a HTML5 conference. HTML5 is important. Browser-based communication is exciting, but the natural ground reality is you can't ignore mobile for any real practical application you guys might be building for WebRTC, even using WebRTC. So mobile has to be something which is taken into account. So what are the problems with mobile? No reference WebRTC implementation for native devices. Although Google propounded it, we don't know when it's going to arrive natively in Android. We only know the browser is supported at this point. So what do you do for native applications? Like I said, Apple has no public stance on iOS. So if you're building a native application on Safari, you'll either have to use a third-party SDK or you'll have to port the code to iOS yourself. So the WebRTC libraries are open source, they're available, but good luck trying to port that over to iOS. It's quite painful. Having done it, I can attest to it. The other big problem, and something you want to think about as you're building an application, is even battery and performance on mobile devices. Let's say you decided native applications were not important, you're willing to live with the experience in a mobile browser. The interesting thing is WebRTC uses a codec called VP8 for video and uses a codec called Opus for audio. Now, most commercial video conferencing equipment is all based on H.264. Most of the mobile devices have chipsets, hardware chipsets for encoding H.264. They do not have chipsets for encoding VP8. Maybe Google will be able to push this and get Android device manufacturers to adopt it, but it's not going to happen anytime soon. And encoding, software encoding VP8 is a very expensive operation computationally. And so let's say you had a very large high quality stream which you're pumping from a mobile device, that's going to drain a whole lot of battery and things like that. So this is again something which you need to factor in as you're building or thinking about your WebRTC application. The other problem itself is, like I said, Safari and IE. Full disclosure, I used to work at Microsoft, and I'm not booted a Windows machine in 5 years, but I have to say they did provide an alternate proposal which made a whole lot of sense. Their alternate proposal was something called the Object API, where they said, as a JavaScript developer, as an HTML5 developer, I shouldn't have to worry about SDPs and things like that and understand this protocol. I should just be able to say, set the resolution, set the encoding parameters, I want a stream. There's no reason SDPs should be a surface API. And they also point out some problems with the offer-answer model. Not sure if that's going to get any traction, but it leads to fragmentation. So you might want to think about what your IE strategy is. One tip I can give you guys is there is this plugin from Google called Google Chrome Frame, which just basically emulates the Chrome browser on IE, which supports WebRTC. So that's potentially an option for IE if you wanted to use WebRTC. But Google also announced that they're going to retire support for Google Chrome Frame in the beginning of 2014. So, no idea where that's going to go. So we spoke about signaling, we spoke about interoperability, we spoke about connectivity. I think that the last point I want to make here is multi-party is again very important. WebRTC as it's designed today is merely a peer-to-peer protocol. That's great if your use case is only peer-to-peer. Most logical use cases, a lot of them, are more than two people, and you need to be able to think about how you're going to handle a sort of multi-party use case. There are one of two options here. The simple, most naive option is to use a mesh of peer connections. Let's say I am connected to 4 other people, so I will publish my stream 4 times to every other participant. So once to every other participant. And so you quickly run into like a fully connected graph like on the left with a whole host of peer connections. Now obviously upload bandwidth is a valuable commodity, more so than download bandwidth, and as you scale the number of participants in a call, this is not a viable solution. There are other problems, but that's sort of the most fundamental problem. The other option for you guys, if you're looking at this route, is again using a third-party solution or building your own media relay server. So one option is to build a media relay server where you are able to pump a stream to a conferencing server or a media bridge or whatever you want to call it, which then redistributes the streams to every other endpoint. And so even though WebRTC is peer-to-peer, this browser essentially thinks that it's connecting to another peer, but what it's essentially connecting to is a server. So you create a series of peer connections, one from each endpoint to a centralized server, and then the server is responsible for routing traffic. Now, for those of you who've written high-performance servers, this is again a non-trivial exercise. The other tips I can give you guys is to maybe take an open source project and extend it. That's one way to look at it if you don't want to look at a commercial sort of alternative. My next topic is also related to multi-party, and I want to give you a flavor of the sorts of problems you might want to think about or solve or prioritize ahead. Is when you're building something like this, there is something called RTCP feedback. Let's say in a peer-to-peer session, let's say I am talking to Lauren, who's sitting here in the front desk, and let's say my subscriber, my download bandwidth was pretty poor. I'm not able to consume her published feed. I, under the covers, can throttle and tell Lauren, can you please downgrade your quality? And this completely makes sense. This sort of RTCP feedback completely makes sense in a one-to-one call. Now, if I'm not able to consume a stream, I will ask you to downgrade your stream. Makes sense, right use case. The minute you go to a multi-party call, imagine what happens as more and more people join. Let's say, just hypothetically, you had a 50-person call and 49 people had extraordinarily good bandwidth, right? You had all the bandwidth you can use, and the one person who joins is on a Wi-Fi network under the bridge or something, and he's going to degrade the call for everybody else. So handling RTCP feedback intelligently and adapting to quality in a multi-party call becomes very important. I don't want to go too much into this graph, but what I would like to show is this is sort of an aggregate bandwidth, the bit rate for each publisher, And here you see a batch subscriber joining. This is a batch subscriber joining based on real world data. And that batch subscriber throttles the publisher and causes the publisher bitrate to tank. Now you can ignore the right side of the graph and why that improves. That's sort of, I just pulled this from one of our internal servers which does adaptation, but you can see the impact of the bitrate going from 200 kilobits to 50 kilobits just because the bad subscriber joined. This is something again which is sort of important to keep in mind. That's sort of the high-level list of considerations I wanted to talk to you guys about, and want to also talk about 3 high-level real-world use cases and show you guys that all these areas I spoke about are not theoretical. They actually are very relevant even for simple applications. The first being an online classroom. Education is the most natural real-time communication app. The minute you want a classroom, you have more than one person. It's rarely like a one-to-one classroom. You will have to give preferential treatment to certain streams. So immediately you go into quality adaptation mode. You have to figure out how do I boost the quality of one stream while lowering the quality of other streams. All of the people might be in the same room, or some subset of them might be in the same room. So you have to think about echo cancellation, audio artifacts, gain control, things like that. So even for relatively simple applications, these considerations become useful. Another common use case we've seen from our partners is what I call the see what I see use case. So I can't name names here, but one of our partners, who's a famous insurance company, wanted to build sort of a use case where, let's say I get into a traffic accident, I whip out my smartphone or laptop or whatever, fire up a browser, and I basically live stream with the insurance representative and show him my car or where it's damaged or something, instead of taking low resolution pictures and then going back and forth and fighting the claim. You could do this online where the insurance agent says, I want a higher resolution picture of this angle or that angle or what have you. Again, think about the kind of complications that introduces. Even if it's a one-to-one and it's peer-to-peer and you could do it with WebRTC, what happens if I want to take a high-resolution picture in the middle of streaming, right? What happens when I upload that picture and it degrades the bandwidth? What happens to the end-user experience? And I need to be able to flip very quickly between the front and back-facing camera seamlessly in the middle of the call. Can I do that without disrupting the call in flight? Again, interesting considerations to think about, which immediately become apparent when you build sort of a real-world app. And finally, I had a demo. The Wi-Fi is pretty bad, so I don't know if I'll be able to pull it off. I can try it. Is robotic companies are very actively in the WebRTC and HTML5 space. So I have here a robot. It's called, it's from a company called Double Robotics. And what they do is it's powered by an iPad. And they are a very simple telepresence robot. With the advent of good 4G Wi-Fi connectivity and cheap and powerful smartphones, robotic manufacturers can actually focus on robots. So I can actually drive it, and we frequently do this in our work where we have people from Barcelona and whatever. Yeah, the Wi-Fi is not great out here, but you get the point. The point is, what I am doing here is this is a HTML5 app purely based on the web, powered on WebRTC, which is actually connecting that robot, and I could be on my desk and I could remotely power a robot and talk to my colleagues in a different office. So this is an example of a HTML5 application to a interesting mobile application using WebRTC. So just wanted to give a flavor of a real world sort of application. I promise I won't hold you guys for too long. So the main point the main takeaway from all of this is WebRTC is clearly a hugely disruptive technology. And it's in its early infant phases, but it's very soon going to crystallize and going to become very relevant. Somebody from Google had mentioned that there would be more than 1 billion unique WebRTC enabled endpoints by the end of 2013. And just before I came to this conference, I was looking at some numbers, and the number was something like 3.5 billion unique endpoints fourth quarter of 2016. So this is a huge phenomenon which is happening in the HTML5 space. And I'm going to quickly run through this. We did a very quick survey of people, mostly in North America and Europe, of software, mostly software developers, asking them, what do they feel about video conferencing, WebRTC. And these are the industries which said they were very likely to adopt something in WebRTC in the next 24 months. Now, the first two are obvious, right? You would expect telecommunications, video conferencing to be obvious. But customer support, education, and healthcare are quite interesting. There's a lot of activity in healthcare applications where it's doctor-patient consulting or doctor, pharmaceutical company, customer support, things like that in real time. And most doctors have iPads and mobile devices, have access to a modern browser. It's going to open up a whole host of very, very powerful and exciting applications. What is stopping movement was basically about 70% of people, even 80, I think, 80% of people said that the market is fragmented, the ecosystem is fragmented. Some browsers support it, some browsers don't support it, some devices support it, some devices don't support it. It's this fragmented ecosystem which is causing problem. But what we do see as a platform provider in WebRTC is that all of those things are converging really fast, and very soon, things are going to get unified around a set of standards, and it's going to become increasingly important, and all of these roadblocks are going to be removed. What's missing, obviously? This is the gist of what you all need to think about as you're building a WebRTC application, is mobile, multi-person, even archiving a recording. Let's say I wanted to record a conference. How do I do it? And so it's a whole bunch of interesting use cases. So this is my final slide, and what I'd like to say, the key takeaway is, when the social web and all of that came about, very few people predicted the rise of companies like Facebook and Twitter, which are like global phenomena at this point. And the same way, WebRTC has the potential to lead to very disruptive opportunities in real-time communication. And if you look at the past, it's always siloed applications. If I want to talk to my grandmother, I have to open Skype. If I want to call my insurance agent, I have to call them on the telephone. If I want to talk to somebody I don't know, I would have to write them an email or whatever. In the new world, we have the ability to build very immersive, fully integrated, seamless real-time communication apps. On the right, you can see, there's no reason why I should not be on. We call it AirCNC, but it's riff on Airbnb. But there's no reason why I shouldn't be on a website where I'm able to talk to the customer service agent. There's no reason why I shouldn't be able to talk to my financial advisor as I'm looking at my stock portfolio on the trading website. I shouldn't have to call them separately or whatever. And there's all these very interesting use cases which WebRTC is going to open up. And I hope you all will build some really cool applications or companies based on WebRTC. Thank you. Happy to answer any questions you guys have, or yes. That's sort of that's an interesting question. So we used to be a Bay Area startup, TalkBox, but then we were acquired by Telefonica Digital. So Telefonica is a huge carrier in Europe. They're like the AT&T of Europe. So this is something which is sort of near and dear to us. I think a lot of telcos are actually paying attention to WebRTC. They do realize that WebRTC is going to change the focus of media transport itself and move it towards the web. couple of years ago, real-time communication on the web was just a novelty, right? You try it out, it'd be cute, but that's about it. But with FaceTime and even things like that, the credibility of online video or online communication is been vastly improved. It's no longer a novelty. So telcos are definitely waking up to it and sort of figuring out the right monetization strategies. I can't say there's an answer here, but they are looking at over-the-top services, over-the-top apps, integration into existing PSTN networks and things of that nature. Yes.
Can you touch on the differences between WebRTC and WebSocket?
Sure. So WebSockets is sort of a bidirectional pipe for data transport, right? WebRTC is a much larger set of APIs and technologies which enables real-time streaming. So the signaling thing, like I mentioned, you could use WebSockets or something over WebSockets to sort of signal and transfer data across peers, but WebRTC is sort of, I would say, it's complementary to WebSocket. So WebSocket enables a certain form of data transport. WebRTC is a whole host of purely real-time communication-oriented technologies in the browser. Yes?
Is there a built-in signaling protocol for WebRTC that you can, write your own code for to bypass, or
yeah.
Is there something built in?
No, maybe I should say unfortunately. Fortunately, there is no built-in standard. So the expectation for the WebRTC from the committee is, how signaling is built in WebRTC is sort of independent from WebRTC itself, and so they don't have a standard. But while there is no built-in mechanism to establish a call, you do have the built-in mechanism of a data channel API to transfer data or signal once the call has been established. So if you look at the pre-call establishment world, no built-in standard. The post-call established world, you can use the data channels API. Again, that's just a mechanism. There's no real protocol in terms of what goes over the data channel. It's completely left to the developer. Yes?
Are there open source signaling servers out there?
Yes, I mean, yes, there are a whole bunch of open source signaling servers. You could use any XMPP server. I think OpenFire might be open source. I'm not really sure. You could use like Socket.io and get your own signaling server up and running. You could use a third-party API like Firebase or OpenTalk or Pusher or PubNub, any of these things.
Well, those are mostly APIs that you can use to build your own server, correct? So, I mean, because I saw that there is Talkbox, OpenTalk.
Correct.
But that is not open source.
Correct. So OpenTalk is not open source. It's a platform which you can build apps on top of, which abstracts out all of the underlying difficulties of WebRTC. If you're looking to host your own signaling server, any existing XMPP server or SIP, like a SIP server or things like that could be used, or you could write your own very simple thing with Socket.io. Or you can, in the ultimate worst case, it's super hacky, super ugly, you could even, you can actually poll and you can still do it if you wanted to. Any other questions? Thank you. I really appreciate you guys staying late. Thank you.